Hi, good afternoon, folks. We're going to go ahead and get started. I'm Yatharth Gupta. I'm a product manager on the Azure Databricks team, and I have here with me Kyle.
Yeah, I'm Kyle Pister. I'm a senior solutions architect at Databricks. I've been working with Apache Spark for about 4 years and been at Databricks 3 years and work on all things technical on implementation of our Databricks customers.
So we're here, we're going to spend about the next 65, 75 minutes talking to you guys about how to build streaming pipelines or applications that could use streaming pipelines with a combination of real-time streaming data and batch data. And we're going to build these applications using a service called Azure Databricks. How many people familiar with Azure Databricks? Oh, that's pretty good. How many people have used Spark?
Oh.
Excellent. So we have the right set of audience here. So we're going to go ahead and get started with some of the common scenarios. I'm sure you guys have a lot of scenarios that you think about as you build these applications with streaming pipelines. We're going to go over some of the canonical ones. We're going to actually deep dive into one of them later in the session where we'll talk you through how to build this end-to-end. We have a pretty cool demo where we have wind turbines and how you can take real-time data from wind turbines and predict if they're going to fail or succeed. We'll talk a little bit about, briefly about what is Azure Databricks for those who aren't aware. And we'll spend some time talking about what is Spark, again, to orient the folks in the audience. We're going to go deep into what a streaming pipeline looks like, what are some of the challenges, and how we are going to make it super easy with Azure Databricks to solve those challenges so that you can focus on your applications and on your business logic. So with that, we'll go ahead and get started. Just some of the common problems, we're going to talk about streaming. It means different things to different people, processing stream and batch data. But what are the kinds of problems that you can address with this? Like, what should you take away from this session today? If you think about a connected car, there's a bunch of manufacturers who want to do hot or warm part analysis. And the common scenarios that they have in place is they have all of these cars that we all drive. They all report back telemetry. And they, as the manufacturer, want to, in real time or near real time, be able to detect anomalies with the cars. So to send the car a signal to go in for a service or things like that. How do they do that? Streaming is one way to address that. Ad tech, this is a completely different field, but think about if you're in the marketing space and you publish ads, you kind of want to know what the ROI on that ad is in near real time so you can make adjustments. You don't want to put an ad and then 30 days later know that it was ineffective or people weren't clicking on it. That's another scenario. In the telco space, so if you're a mobile operator, one of the places we see them innovating is they're doing a bunch of fraud detection in real time. People sending fraudulent SMSs, so applying some machine learning, trying to figure out who's sending them, why these are getting sent. Industrial automation, this is one of the biggest use cases that we see, where most of the factories, they have a bunch of machines, and all of these machines are sending sensor data. And efficiency is paramount in these industrial automation scenarios. So what they want to be able to do is they want to be able to detect in real time whether something is going to fail, assess the impact of that, and do some sort of preventative maintenance on those devices. And the demo that we're going to walk you through, and our hope is that after our demo, you should all be able to build an end-to-end pipeline with wind turbines, hopefully. So the demo is going to show that. Application telemetry is another place where a lot of people do real-time analytics or streaming analytics. So how many folks build client applications in the room? So I see a few folks, plenty of folks. So if you're building client applications or front-end applications or even server-side applications, these applications generate telemetry. And you might have a need to analyze the logs, the real-time logs that are coming out of these applications. That is also a streaming scenario where you have data flowing in. You want to run machine learning, or you just want to analyze that data in real time and get to insights. The demo, like I spoke about, our demo is going to show you today, which will come towards the end of the session. Wind turbine with 7 or 8 sensors generating data. We're going to take that real-time data, clean it up, We're going to do some joins with some batch data. So, they're just generating sensor data. We're going to join it with some data about the wind turbine itself. We're going to apply a machine learning model. And then we're going to post it in Cosmos DB. Folks familiar with Cosmos DB? Usually that's 100% yes. Yeah, so we're going to post it in Cosmos DB, where you can build a client-side application using Cosmos DB to build chatbots or to build dashboards of proactive alerts using that data. So let's get started. What is Azure Databricks? From show of hands, I kind of understood that several folks have heard about it. Folks are familiar with Spark. Essentially, Azure Databricks is our version of managed Spark. So if you guys have used Spark, what you'll find is Spark is open source. It's pretty powerful. It has a very rich and thriving community. But it's hard to get set up with it because it was built for on-prem. You buy a bunch of machines, you install Spark on there, you get a command line. With Azure Databricks, we take all the DevOps out of Spark for you. So you log into the Azure portal, you can click a few buttons, and you get a Spark environment that can scale from 1 to 1,000 nodes in a cluster in a matter of minutes. And we integrate all the tools that make you much more productive, eliminating any sort of maintenance of clusters or managing them or any other DevOps things that are required. The other thing that we do is we also understand that technology doesn't live in a vacuum. Kyle and I, we work on Azure Databricks, day in and day out we work on Spark. But in the real world, you're going to have to read data from somewhere, right? Data has to come into Spark from somewhere. It's going to come from Azure Data Lake Store or Blob Storage, wherever you might house your data. It might come from Event Hub or Kafka through HD Insight. You got to connect Spark to all of these things. We have pre-built these things for you in Azure Databricks. So you write a couple of lines of code, you can read data from anywhere. At some point, you're going to want to orchestrate this end-to-end. Like you're going to have service A, service B, service C. You're going to want them to work in tandem. And we have Azure Data Factory that we've integrated so you can orchestrate this end-to-end. And then we have connectors for SQL DB, Cosmos DB, because at some point you're going to want to put your data or read data from those data sources. So we have connectors for those. Some customers, depending upon the scenarios, you might want to do BI analytics. So we also have integration with Power BI. So if you have data in Spark, you've analyzed that data, now you want to visualize it, you can do it in Power BI. One of the other challenges with open source frameworks, I love the open source frameworks, and Spark is like very powerful. But as you get into enterprise grade use cases, one of the challenges is it doesn't integrate with security. So most of these frameworks come with Kerberos security, and most enterprises are using something like AAD, Azure Active Directory, or some sort of domain controller that works with Azure Active Directory. In Azure Databricks, when every user logs into the Spark environment, they log in with their Azure Active Directory credential, which if you are in the IT management space, or when you guys go back and talk to your IT managers, it just makes their life simple. Like it's an easy check for them to do and get started. A little bit of, so Azure Databricks, it's the super managed version of Spark, right? And it comes with a bunch of efficiencies that we have built in that's not available in open source Spark. But what is Spark, for those of you who may not be familiar? Spark is essentially a cluster framework. So what happens is, in a cluster framework, you can take your workload and divide it across multiple machines. So let's say you want to analyze a megabyte of data. Well, you can do that on your PC. You want to analyze a gigabyte of data. Well, you could do that on a powerful PC mostly. But let's say you start getting into, I want to analyze terabyte or petabytes of data. You cannot do that on one machine because those machines aren't that big in most cases. A cluster framework allows you to have several machines that work in tandem so that your data is being analyzed across multiple machines. And the advantage that we have here is that these can scale up or down. Because it's on the cloud, you don't need to buy those machines. We'll scale them up or down for you. So you wrote a job to analyze some data. It was 1 gigabyte of data. You could do it with 2 machines. Tomorrow it scaled up to a petabyte of data. You can just scale up your cluster and only pay for what you use. You don't need to pre-provision anything. Spark offers, so it's a general cluster framework, but it offers a number of things. It offers you the ability to do machine learning, and we're going to touch a little bit upon it. That's not the focus of our talk, but happy to take questions on it. It allows you to run analytics queries on data, so you could do a bunch of Spark SQL queries. Most of our focus today is going to be on streaming. So it can take real-time streams and it can analyze them, and that's what we're going to focus on, and it can do graph computation as well. So this is sort of how any Spark program works. You write a Spark program, you can write it in Python, you can write it in Java, you can write it in Scala, you can write it in SQL to a large extent. You write it, you submit it to the driver, which takes that program and then chunks out the small pieces of data that are on each of these worker nodes, and the analysis is done on these worker nodes. And the way this magic happens is through something that's called a data frame. A data frame is conceptually a table. So whenever you're reading data into Spark, you can read it from CSV files, you can read it from SQL, you can read it from Cosmos DB, you can read it from many different formats. But you put data in a data frame, and once you put data in a data frame, Spark knows how to parallelize the operations on that data. And if that seems too much, look at how simple it is to put things in a data frame. I have a CSV file here, a few lines of code. I'm loading that into a data frame. I mention this because as we go through the rest of our presentation, the concept of data frames is going to come up over and over again. So again, what we have done here is we've taken a CSV file. Imagine this was a 1 petabyte CSV file. So you will want it analyzed across maybe 100 different nodes. If you put it in a Spark data frame, every time you apply an operation, it's going to happen parallelly across those 100 nodes. This is what a data frame looks like. So it's conceptually a table. You take any data, you feed it into a table, you give it a schema, and then you can perform all sorts of operations on this. So with that, let's start to talk a little bit about streaming. One of the challenges with streaming is, building these pipelines and doing stream processing is hard. It's not hard because your business logic is complicated. It's hard because of all the things that you need to put together to build a robust pipeline. Imagine if every light in this room was emitting, some sort of value, and you had to build a pipeline to consume those value. Writing your business logic should be really easy, right? You want to find out if the light is turned on or off, and if it's turned on for X number of hours, you do something. But building that pipeline is hard. Here is why it's hard. Data often comes in complex formats. So when I talk about these light bulbs over here, the first thought that comes to my mind is, hey, light bulbs emit data in some sort of format, I can just consume that format. In the real world, it doesn't work that way. Like when we work with customers, and the examples, I won't name customers, but the examples are all real here. When we work with customers, we find out that in the real world, what happens is that these sensors have been built over the years. Not all of them emit the same kind of data. They all emit data in different formats, with different frequencies, with different reliabilities, with different SLAs. Then companies go and buy other companies and merge together. Now, the problem multiplies. So you got to figure out how to deal with this complex data. This data can come in dirty, it comes in late, it comes in out of order. If everything came in perfectly, it'd be easy to build one. Second thing is, you got to deal with complex workloads. If you just want to figure out when the light is turned on and off, that's a simple workload. But what if you wanted to run a machine learning model? Are you going to start from scratch, or would it be easy to use something that already exists? And then you have complex systems. So we spoke about formats, but now you got to deal with a bunch of systems, right? How's your data coming in? Some data comes in through Kafka, some comes in through Event Hub, IoT Hub, some might just come in through raw files because it's an antiquated system. How do you store all of this data? So what we want to do is we wanted to build something where you do not have to reason about how to do all of these things. We want our customers to focus on their business logic. You should be able to write simple, human understandable queries that says, show me all the lights that have been turned off, and you should be able to get an answer. And the backend system should be able to take care of all the problems that I highlighted, right? Like converting data from one format to the other, dealing with out of order, with late data, things like this. this is what we do. So this is what Spark does, and with Azure Databricks, you get a super managed version of it. Here is what a traditional data analysis pipeline looks like, right? So this has existed for many, many years, where you have data that comes in. It's usually dumped as files, and people write jobs on this data. They might write jobs using Spark, they might write jobs using a different framework of their choice, and after hours of manipulation, this data goes into a table. There are challenges, Some of the challenges is it takes a really long time, and that seemed to be acceptable for a lot of use cases. But as new use cases emerge, there is a need to get to those insights very quickly. The business is demanding that, as data comes in, we should be able to analyze it in real time and be able to react to it to get better efficiency. So what we do with Spark Streaming is we use very similar constructs, whether you are using a stream or files or any kind of data. In Spark, you take a data frame, you point it to your source data. That could be a stream, that could be a file, that could be one of many other objects, and any analysis you write on top of it is going to be virtually identical. You could write a SQL query on a streaming data, and we'll show you an example of it, which keeps on updating in real time. Like data is coming in, you just wrote a simple SQL query that people are familiar with, and it keeps updating the results. That's how powerful this is. So we talk about, how do you do this with structured streaming? At a high level, structured streaming consists of three things. It's high level APIs. So I spoke about Dataframes, datasets, and SQL. These are APIs that you can apply to Dataframes. And they're the same APIs in streaming and in batch. So let me give you a concrete example. If you wanted to score an ML model, and you wanted to use input data from a file, or you wanted to use input data from a stream, it would be the identical APIs, and we're going to show you that. We have event time processing, so we have built-in functionality to watermark data, to deal with out-of-order data, because these things are hard for you to build, and this is a common problem that every one of you is going to face. So we didn't want you to work on fixing this. We wanted you to focus on your business logic. And the last one is the end-to-end exactly once. And what this means is, as you build streaming pipelines, think of it as a job that's continuously running and it's processing data. At some point, that job is going to fail for a variety of reasons. And there is a lot of work that is required for you to sort of go back and figure out exactly where it failed and process from the next point forward. That's a complex problem to solve. So with Azure Databricks and structured streaming in Spark, that problem gets solved for you. Again, you get to focus on your business logic. So we'll switch to sort of a very simple pipeline, just to explain some of these core concepts, right? So what does a streaming pipeline look like? What are the different operations you need to perform? You have to be able to read data. You have to perform some stream operations. You might want to output data. Most people output data, and you might want to do long-term analysis on that output data in addition to the stream operations. To read streaming data, we support the following. We say that streaming data typically comes in through some sort of stream framework. If you are in the open source world and you use Kafka, we have support for HD Insight Kafka. That's a first-party offering from Microsoft, so you can run Kafka on Azure through HD Insight. If you wanted more of a PaaS offering, you could use event hubs. If you wanted much more richer IoT scenarios, you could use IoT hubs. Or hey, if you had an old system which was just writing stream data to files, we'll let you read from files. Reading data into a data frame is super simple. Like, we were trying super hard to make this slide more complicated and more engineering, but it really comes down to something as simple as this command. You create a data frame, you say spark.readStream. In this example, we're using Kafka as the streaming engine. So you're reading from Kafka. Kafka has this concept of topics. So Kafka is a pub-sub streaming framework where publishers publish into Kafka and consumers read out of Kafka. And what they publish is a topic. So your stream would have a topic name. In my case, I'm subscribing because I would want to read from the stream. I'm subscribing. I give the topic name. I give some offsets. And there you go. That is all you need to do to start reading a stream. There are several other options where we don't go into some of the advanced options, but we're happy to take any questions towards the end if you have about them. But you could do multiple operations in the read itself. You could do some group and aggregations. You could also rewrite the stream. We'll talk a little bit about that. Once you have read the stream, so you have all this data that's coming in, you've read the stream, now you've got to perform some operation on the stream. That's sort of your core business logic. And I've sort of divided the operations into a couple of core concepts. You can perform basic operations like selections or aggregations, where you're saying, hey, I have this stream coming in from all the light bulbs in the Washington State Convention Center. I would want to know at any given point of time how many are turned on or how many are turned off. Or maybe you want to do something more advanced. How many have been turned on for 12 minutes? You could do join operations, following my light bulb, because that's all I see from this side of the table is light bulbs. You could do join operations where you could say, show me all the light bulbs, but there is another sensor in the room which shows room occupancy. So show me all the light bulbs that have been on where the room occupancy is 0. So you could do some join operations. You could do window operations, which is you could say, I want results over the last 10 minutes or over the last 15 minutes. And you don't need to build this logic. You just need to say, use this window function. You could do machine learning, which is the coolest part, because the applications that we see from our customers are just phenomenal, where they're getting data, they've built machine learning models, they're applying it to real-time data, and before their field calls them, they know why the field's calling them. Like if in the wind turbine example that we're going to walk you through, the real world use case is that if some components are going to fail, some engineer is going to call the operations office that something's going wrong. The operations office is going to know ahead of time what exactly happened. You could also trigger operations. So you could do something as simple as when a stream is coming in, depending upon what analysis you wrote, you want to send an email or fire up an alert or run any custom function. Again, simplicity is sort of the core, the foundational part of our service. Here is what it takes. Like you have an event data frame. So we showed you how to read events into a data frame. You take the data frame, you put a where clause, you potentially join it, you do some group by. On the left-hand side, and sorry, my slide's not updated. On the left-hand side, it's Python. On the right-hand side, it's using SQL. You can mix and match these languages within Azure Databricks. So you get the results. And when we show you this, you'll see how the results update in real time. Stream joins is something that is very new to Spark and to Azure Databricks. So you could have two kinds of joins. You have streaming data. You could join it with a fixed table, or you could join it with another stream. So Kyle, if you want to explain this a little bit.
Yeah, so Spark for a while has supported streaming with batch joins. So say that light bulb example where you have stream coming in of every state of the light bulb, but you have some lookup information about each of the bulb, maybe the manufacturer that you want to normalize the schema. Well, the stream batch join you can pull from Cosmos, you can pull from another table that exists on data lake storage. But what's been harder is stream joins. So let's say you have two streaming data sets coming in, and you want to join those two together. So why that's difficult is the streams don't come in at the exact same second. They may come from different sources, and so you need to buffer the data or store that data state for some period of time so you can join on those two columns. So most join operations, other than full outer joins, are now supported in stream joins. So one of the examples we talked about was ad tech. One of the canonical examples for this is you have an impressions, every ad served, maybe on a website, and then clicks. Which of those got clicks? So those are usually two different systems that report those. And you need to keep the impressions for, say, a day or so, because clicks can come in for up to 24 or even hours later. And then you join those to say, hey, this ad impression did get a click. So these stream joins become very easy to reason about. And Spark takes care of handling all that state that needs to be stored, all with those exactly one semantics. So no data is missing or no data is duplicated.
The other operations that I spoke about was generating alerts. So again, simplicity. You're reading the stream. You want to filter when clicks are greater than 9999 and send an email to marketing. The new email alert is actually a user function. So you can write any custom user function. It could be PagerDuty. It could be email alert. Whatever you wanted, you could write and build that. Our focus has always been on your business logic, and we take care of the rest. Once you do the stream operation, so you read the stream, That was pretty simple. One command to read the stream. Depending upon what your business logic is, most of that happens in stream operations, aggregation, machine learning, whatever you want to build over there. At some point, you're going to want to rewrite the stream. And there are two primary reasons why you want to save this streaming data. Either you want to save it for long-term BI analytics. So you have the stream coming in, and at some point, you'll have somebody go in and look at historical data. You want to save it to a file for that. Or the second reason is that you're building a pipeline and you want to take part of the stream and send it to somebody else. Right? Let's say the stream came in with dirty data and with 700 columns. And your downstream engineer only needs 5 of those columns, and he expects the data to be clean. You could reroute that data back into a stream. You can also, and these aren't as frequently used, but you can also output to memory or to console for debugging. You could potentially output to a for each iterator if you wanted. So here is what filtering the stream and restreaming it back. So you read the stream, you say event type view, you filtered the stream, and you rewrote the stream back to another stream. So think about if you're building a pipeline job. Big stream comes in, you do a bunch of filtering, you restream it out, the next engineer down the line picks that up, he does his work. Chaining of these things, again, very simple. We show Kafka in a lot of our examples. We try to cover all our bases. So in our demo, we're going to show Event Hub, but in the slides, we show a lot of Kafka for streaming. You could also write data to disk, which is something that a lot of our customers do. Is they'll take the stream, they'll do the stream real-time operations, but they'll also write the data to disk or to Azure Storage or Azure Data Lake Store, which they're going to use later on for an analytics. So a BI guy comes in and he looks at the history for the last 12 months, or a data scientist comes in and he builds a machine learning model based on historical data, which can then be scored on real-time data. That brings us to the analysis part. So once you have written this data to disk, you can very easily query this data. You can write simple SQL statements directly on the stored data. So this is not analyzing real-time data. Now we're analyzing stored data. And you can just, as data is getting written, if you keep on running this query, you'll keep on getting updated results. And you can window this over a long period of time. This particular operation has some fundamental challenges in the big data space. And if you're familiar with the big data space, what happens is when you write in Parquet, you're constantly writing small files and you're creating partitions, which makes some of these queries longer or not optimized. And what we have done here is we've introduced something called Delta, which is a table format, which allows you to write this data and get rid of all the inefficiencies that would exist in a big data system. And that is something that is exclusive to Databricks. So it's available on Azure Databricks, but it's not available on Apache Spark. So that's sort of one of the things that differentiates Azure Databricks. In addition to being managed, in addition to being having the ability to auto-scale, auto-terminate, a lot of those things, some of these high-end features are only available in Azure Databricks. So Kyle, if you want to talk a little bit about Delta.
Yeah, that's exactly right. It's a new optimized format for storing data on storage or data lake. It's a better way to deal with Parquet for both batch and streaming updates. In the streaming example, it improves performance. So it allows the data engineer, or someone who's writing this data, these streams, to write new data every few seconds. So those querying it can have data that's up to date. You don't need to wait 15 minutes or an hour to write files to make sure they're appropriately sized for query speed. So it increases that performance of being able to write the optimal file sizes. It includes other things that make it easy to manage. So it handles failures. It also adds a secondary indices on top of the data over partitioning for those who are familiar with Spark SQL or Hive-style storage of data. And it maintains the metadata about it. So there's no MSCK repair table or inserting partitions to maintain the metadata of how your big tables are stored. And it improves the reliability. So it's transactional guarantees. So if, say, your stream's writing and something fails in the process, you haven't littered your data set with dirty data. Those files will automatically get cleaned up. and then the new time it picks up from the latest offset, say from Event Hubs or from Kafka, it'll just write that new data to the source system. So again, you're guaranteeing that exactly one semantics, so no one's querying data that's corrupt. This also allows us to do certain things like upserts. So not upserts for maybe like a transactional system, but if you need to go back and change like the type of a data format. Maybe you did it as a double, but it really should have been an int. You can go back and make some of those changes to update the schema of the data set in Parquet that you've stored on storage or data lake.
So we're gonna switch over to our demo here. But before we do that, just to set the stage of what we're going to show and what we're going to solve, because there's a couple of different components here, and every part we believe is powerful. We just want to make sure everybody gets all the different steps that are going to be involved. First thing we're going to do is we have wind turbines. We have thousands of wind turbines that are deployed. All of these wind turbines have sensors in them, and these sensors are emitting data. We're going to read this data. We're going to store this data. We also have historical knowledge on which turbines have failed, which turbines have not failed. We're going to use that to build an ML model on the batch data. Then we're going to take that ML model and apply it to a real-time stream, so you can see in real time, you can predict if a wind turbine is going to fail or not. The way we've built this demo is you could essentially replace the wind turbine with anything else, right? At the end of the day, everything is a bunch of subcomponents that has a bunch of sensors that are emitting data. You could replace it with any one of those and use the same system. We're going to write that data then to Cosmos DB. So if you're an app developer, if you're a front-end app developer or a web app developer, you could then use those predictions to build smart applications. We won't go into that part of building a client-side application, but imagine if you had a database, an operational database that said, here is your list of wind turbines, and these are most likely to fail in the next 10 minutes. You could build smart chatbots where when your field comes in and says, does this turbine need maintenance, it would automatically tell you that it's about to fail or this component's about to fail. So with that, we'll get started. And Kyle, would it be helpful if we could show a little bit of how Databricks is, Azure Databricks is set up? Like how do you create a cluster and notebook and some of those concepts?
Sure. Switch the view. Okay, so I already have Azure Databricks open and deployed. It's easy as creating it in your Azure portal from your subscription within a click of a button, and you'll have an Azure Databricks environment spun up in whatever subscription your target subscription is. And it takes about just 3 minutes to provision this environment. And once it's provisioned, you get to log in for the first time. So the initial login, all through AAD, will bring you to this screen for the particular environment. Once you've logged in, Databricks isn't costing you anything. There's no cluster spun up. You have to go create a cluster to do any of these work.
So I want to take a moment to pause there, and for folks that are familiar with Spark, if you have deployed Spark on-prem or on other cloud services, one of the things that you'll notice is that you got to start a cluster before you can do anything. And the moment you start a cluster, you got to plan for the cluster. You got to know how many machines you want, and you got to start paying for that. We built this for cloud first. We know that that's not how people think. We know that that's not how people operate. I haven't found a data scientist or data engineer who, without experimentation, can tell me the exact size of the cluster. So we wanted you to be able to come into our environment, write code, start small, and grow from there without having to do a bunch of DevOps and planning ahead of time.
So I'm going to walk through today mainly the UI of the portal, but for those who don't like to use any UI tools, keep in mind there's APIs behind almost everything I can do. So if you want to automate any of the things I'm showing in the UI, that's altogether possible in terms of scheduling jobs, writing code. So keep that in mind as we walk through this. So the first thing I want to do is I'm going to navigate, up at the top is my workspace. The workspace is a place for me to store my projects, which allows me to store code as well as libraries that have been added in. These could be Java libraries, Scala libraries, Python libraries, R libraries, or any of those code. In this particular case, we're going to walk through that wind turbine example. So I have that in this IoT folder. And the first thing we want to do is we want to start streaming our events. So as we can see up at the top, this is a Scala notebook. I'm already connected to a cluster that I've spun up. I'll do that I'll show you how to create a cluster here in a moment. And then I can begin to write commands. So we want to stream from event hubs. But before we start to dive into that, let's just create a new blank notebook. So this is really where I can create a notebook, which is a way for me to execute code against the cluster interactively. So let's go ahead and create a new notebook. I get to choose the language that I may be most comfortable in. Maybe I'm comfortable in Scala or Python or SQL or R. I get to choose the language I want, and then which cluster I want to execute it against. So what's really great is you could have maybe a small cluster up for development on a sample of data, and you want to test it and move it to prod. You can do that with the click of a button, since the code and the data are decoupled from the actual compute itself. Or one of the key things which we'll show you is, you notice these are two different versions of Spark. So there isn't big upgrade cycles. You can actually choose the different version you want. So maybe you have a prod job that's running on an older version. You want to test some of the new features on a new version. You can test that before you move that prod pipeline over. So I'm going to choose one cluster, this query cluster. And this creates now a blank notebook. This one is Python that I can begin to run commands. So I can run normal Python commands like it was my terminal. I can even switch languages, say SQL, and say show tables. And so these aren't tables actually stored in Databricks. These tables are just metadata that's pointing to data wherever it may be stored. Most commonly, the way tables are stored on our Azure Storage or on Azure Data Lake, but this could also be pointing to tables in, say, SQL DW or Cosmos, where you may persist those data for others' use cases. The notebooks themselves are really nice because they have permissions. So I can prevent certain sets of codes for different users to have permissions on this. So right now it's only Yatharth and I in this particular environment. So maybe I'd give him read access because I want him to see the code that I've written, but I don't want him to break anything. I can give him those abilities to do that. Or maybe I do want to let him edit it or manage it and invite others. I can give him that ability to do so. And so I can do this both for individuals as well as with groups. Another key things that help with development is revision history. Right? When you collaborate in notebooks and you aren't doing maybe a proper CI/CD, people may come and change things in an ad hoc notebook. And you can see those changes in that revision history directly in the notebook. And so I can restore to different versions and see what's actually changed. So that's a notebook at a high level. So to switch back to my streaming events, let's walk through this first one, and then we'll switch gears into the cluster. So this first step is that beginning of that workflow. We really want to read the stream where we're pulling the data from. So the reading the stream is two separate use cases. There's the streaming data, which is coming from our Event Hub sensors. So in our case, this is going to be Event Hubs. But like Yathar said, this could be Kafka, this could be files on storage, et cetera. And then, of course, we know streaming isn't the only data source in an organization. So there's traditional data sets that we may want to join. ERP data, inventory data, maybe maintenance logs. And so that may be coming from different sources. Maybe we have Azure Data Factory that's pushing that data to storage in its raw format. Or maybe this data is from a SQL server. We can pull those data and cleanse that data to create it in that optimized Parquet Delta table that's available. So we're going to walk through those initial steps. So let's start with the Event Hubs. So the first thing is the Event Hubs library. Both the Spark team at Databricks collaborated with the Event Hubs team to make sure this connector was reliable. So those teams work closely together to make sure it's optimized for performance, reliability, as well as the style guide that's best for Spark. And Databricks makes it really easy to manage that library. So I have that library here. I've just uploaded it from Event Hubs. And I get to choose which clusters I get to attach it to. So this allows, if you were to do this on your own cluster, you'd have to download the library, figure out how to get it installed on every node. And it's a non-trivial task. Or you'd have to bundle it up in like an Uber jar and just submit the whole application to the cluster and hope it worked. With Databricks, you can install those libraries with the click of a button, either by uploading your own libraries, such as a jar or a Python egg, or you can pull from sources like PyPy or Cran and directly download those, and Databricks will automatically handle the dependencies. And then when you choose to attach it to a cluster, it'll attach it to that library to every one of the nodes for you automatically. So for this Event Hubs connector, which we need to read from Event Hubs, I've attached it to the production cluster that I'm going to be using. So if we switch back to my streaming events, now that we have the library, we can build our connection string. So this is our Event Hubs read key. So I have this stored in the Databricks secret store, which stores that secret to read that Event Hubs key. And then I'm building the connection string, which just passes in the parameters that Event Hubs needs to read from. Once I've done that, I get to define my streaming data frame. So all I need to do is say read stream. If this was a batch job pulling from storage like the CSV, this would just be read. So it's a one-line change and changing the format to Event Hubs rather than CSV and passing those parameters. So if we go ahead and execute this, this will send this to the cluster to execute and run the command. And so one of the things about Event Hubs is the data is sent as sort of a key value store. And the way that's stored, it's in binary format, as well as metadata about the stream. So really what we want to do is we want to get that binary format into a string that we can manipulate. So all I'm doing is a simple operation to convert that body from binary format into a string. So I have that streaming here. So you can see what that body looks like. So now I do have it in a string format. It's not very nice. It's a JSON object, so it's not easily human readable. In a string in one particular column in a data frame. So Databricks also provides some nice metrics. So we get to see how much data is coming in and whether we're keeping up with it. So the input rate's how much data is being fed to us from Event Hubs. And the processing rate is how fast the Spark cluster, the Databricks cluster, is keeping up. So in this case, we're on average higher than the input rate, so that's a good thing. So really what we want to do, though, is we want to convert this JSON object into a more standard schema, more like a table, so we can do some analytics or manipulation to that data. So what this data contains is the different sensor readings on these wind turbines. So different vibration sensors and speed located at different points and gear ratios on top of that sensor. So I know what that schema is for my particular wind turbines. So I'm going to go ahead and create that schema. They're double types for most of the sensor readings. The turbine ID is a string, and the event timestamp is when that event was actually produced out in the field. So I'm going to go ahead and pass that schema into a data frame. So again, converting that body from a string, passing it the schema that we just created, and extracting those fields so we get a more of a data frame which has these schemas rather than one string body text. So I'm going to kick that job off, and now we see a much better table view that we would expect on our data. The data is not a JSON object. It's nicely split out. And so new data is going to come in and update as it comes in, and we get to see this table is updated 5 seconds ago, and it's going to keep up and process that data as it comes in. So this is good. But maybe I'm a little more comfortable in SQL. I want to do some analytics on top of this data set. So I can real quickly convert this streaming data frame into a streaming SQL table, Spark SQL table, where I can run normal SQL analytics on it. So if we have the count here, we get to see that this is a streaming table that's updating every few seconds. And if we see this number, it's updating every time new data comes in. So we got ending in 192. And then in about 5 seconds, 2 seconds, it updates in 251. Now it updated again. So the data is updating continuously. So if you want to power real-time dashboards to see certain things, like maybe we want to see how many events we're getting on each individual ID, we can get that table view where the numbers will update. Or we can convert this into a nice visual streaming visualization where you can get those counts based off of each one of the IDs of our turbines out in the field. So this is great, but really this is the raw sensor data. So we actually have more lookup information or a lookup data set that we want to join with the stream. So the next thing that we've done some transformations is we want to do some more advanced transformations like a join with a different data set. So we've already transformed our Turbine ID maybe from our ERP system, and I'm going to load that in. It's in Parquet format, already located on Azure Storage for me. I get to see the format of that data frame here. And then I get to do a display on that so we can take a look at what that looks like. So this is going to be a relatively small table, that just contains information about the ID, maybe who manufactured it, the capacity of each individual asset, and then where and what site that turbine's located. And all I need to do is to do this join is I just say streaming Dataframe, so that's our streaming sensors, join it with that lookup table, Dataframe we just created, and then the key that it joins on. So a very simple one-line command, and Databricks takes care of the rest of doing that join the most efficiently as possible behind the scenes.
I mean, just to kind of think about what we just did, this is where the power of Spark and Azure Databricks comes in. Using the almost identical commands, you took data that is streaming that's continuously updating. You took a field from there, joined it with a batch data set, and now you have this updating in real time. And you can perform all sorts of operations on this, starting from basic SQL queries to advanced machine learning.
So now we have the data the way we want it. We need to store it so other people in the organization, or even myself, can go actually access it. So what we're going to do is we're going to store it in that Delta format we talked about. So this is optimized Spark Parquet table that's optimized for storage on Azure Storage or Data Lake. It's good for streaming, which we're doing here, but it's also good for batch processing. And like we talked about, it has increased performance. It makes it easier to have reliability on the data set and transactional guarantees. So to do that, I'm taking that joined streaming data frame we just created. I'm repartitioning one. So what that means is I have a cluster of all the events that come in. I'm pulling it into one file. So each 15 seconds, I'm going to write one file to Azure Storage. And then there's this checkpoint location. So this checkpoint location is really where a lot of the magic happens, where Databricks keeps track of that offsets. So let's say we were running this in true production, and we wanted to maybe update our code, or we wanted to update Spark versions, or maybe even the application crashed and needed to be restarted. No problem. You're going to continue exactly where you left off, and Databricks will check at that checkpoint to figure out where in the offset it was on event hubs to make sure no data is lost or no data is duplicated. So this checkpoint location guarantees those commits of the data to the data tables to be queried. So as long as you have retention policy in event hubs or Kafka or files somewhere else, there's no need to worry about lost data. Once that's done, I'm going to go ahead and just create a Spark SQL pointer or a table that points to that location. So then I don't need to know exactly on storage where this data set is located every time I want to go query it. All I'll have to use is this sensor reading name. So now that we have the data coming in, we wanted to begin to do analysis on it. So effectively what we've done is we've done this on the left, the green box with the ETL engineers or data engineers, and created a single source of truth of our data located in one environment. But what's really nice about this is I get decoupled storage and compute. My data engineers can use one prod cluster, but now myself, maybe I want to do analytics on this or machine learning. I can do this on another cluster that isn't going to impact my production workloads. So I can spin up another cluster, and since the data isn't persisted on these nodes themselves, the data is persisted on Azure Storage, I can use that data. So you can see up above, I'm actually using a different cluster called Query Cluster. So let's go take a look at the clusters page. So I'm going to switch gears and go from my workspace to the clusters environment. So you can see here I have these clusters up. So we have interactive clusters as well as production jobs clusters. And you can see we've been running that first stage on my prod cluster, which is 9 nodes. And I have my query cluster, which we're going to use here on this next step, in my query cluster. What's nice about this is I have some others that have been terminated. So these are not costing me anything. The VMs have been terminated in my subscription. I get to see I terminate it. Maybe this one timed out. And I could restart these if I wanted to. Or I could create a new cluster from scratch. Maybe I wanted to create an ML training cluster. So I can go ahead and give it a name. We have 2 types of clusters options. Serverless pools, which are really designed to be shared. And what serverless pools do is allow it to be shared across multiple users when you don't know, as an administrator, when people are going to be hitting that cluster. So we can set a minimum number of nodes and a maximum number of nodes. And Azure Databricks will dynamically scale based on that individual workload. So that way, if you have 10 people who are hitting the data set, it'll scale up to 20 VMs. But on the middle of the weekend, when only one person may be writing a small query, it'll scale back down to those minimum number of nodes, so it's not costing you a lot of infrastructure behind the scenes.
And that's where, in traditional Spark deployments, DevOps comes in. Because what happens is when you go and try to deploy Spark or any cluster-based, analytic solution, somebody in IT is going to ask you, what size of a cluster do you want? Let me know ahead of time and kind of prove to me that you're going to use the cluster to its full potential so we're not wasting money. That calculation is completely eliminated here, and you get sort of this runtime elasticity where things grow and shrink as needed without you having to do anything.
On the standard cluster, you have a few more options. You get to choose the runtime version. In the serverless, we're picking the best runtime version that's optimized for sharing. We have a bunch of features as well as Spark configurations for sharing. In the standard cluster, you get to choose the version you want. So this is where it's really easy to switch between versions if you have some workloads that run on some Spark version or even a different Python version, say Python 2 verse 3. Or you want to test the new features. Structured streaming is adding a lot of new features in each new release, so you may want to test the new features before you move it to prod. So you can get access to, say, beta releases before they're available, so you can begin testing. So that's what this 4.1 beta is. And you get to choose the VM types you want. So the best default, if you don't have a strong opinion, is these general purpose. They have the best, kind of well-rounded memory, CPU, and disk for Spark. But if you want to go optimize, maybe you have some reserved instances you want to use, or maybe you want to optimize for cost and performance, you can choose memory-based, CPU-based, disk-optimized instances, and the number of nodes. So maybe I want a 10-node cluster. From here, I get to choose auto-termination. So it's on by default. So with these interactive clusters, and something I do myself all the time, is you may spin up a cluster to do some work, and then you go home for the weekend and you forgot something because someone invited you to happy hour. You might leave a 100-node cluster up for 2 hours, really isn't that expensive, but you leave it on for weeks or a weekend, it can start to add up. And this auto-terminate automatically terminates clusters that are inactive. So if a Spark job isn't running in the background or people aren't submitting commands, this will automatically turn down the VMs. And then when you come in the next day, it's easy as hitting play on that terminated cluster here to restart that cluster with the exact same configurations. So switching back to our analysis, so now we have a new cluster set up. We had our prod cluster doing ETL. Now we have our query cluster. We can start to do some SQL. So I have a SQL notebook here because that's what I'm comfortable with. It could also be from Power BI or other BI tools you guys may use, or even a SQL workbench. You can do these SQL queries. You can do a select star, just like you would, and it's ANSI SQL on top of the data that we just stored on Azure Storage or Azure Data Lake, in our case, Azure Storage. And the data will update. So I'm on a separate cluster, and so since we're streaming that data in, if I do another count on this, I ran this a few moments ago, and what do we have? 5,287.1. The new data's come in. So every time I run a query, I'm going to get the latest data that came in from that stream. So if we go back, we're writing new data every 15 seconds. So this is a really nice thing. So rather than waiting a whole day for my ETL jobs to run overnight when the data comes in, I get the data from, as an analyst perspective, in seconds. So I can make decisions in real time or look at things in real time, and I'm not impacting those prod workloads. So what we want to do is we have some other information about the turbines. We have some maintenance logs called Turbine Health. And if I just do a quick query on that, it's a small table which says which IDs were damaged or healthy at any given time. And I'm just going to join those two. Since I knew one went down, what we really want to do here is we want to predict when our turbines are going to be, start to get in an unhealthy state. So we can go out and do maintenance before they really drop in energy production, or even worse, we have to shut them off. As an energy company, we paid a lot of money to have these assets up. And the higher uptime there is, the more energy or more money we're going to be producing. So I'm going to identify or join with our sensor readings we've created, this turbine health. And if we take a look at it, I can do that join on this view. So just creating a view, which is a logical view of joining those two. And we get to see kind of the status of each of these turbines. So I'm not going to spend too much time on the next section. This next section is how we use that information of whether a turbine was healthy or not to create a binary classifier. You want to intro this?
Yeah, so essentially what we're doing here is we're getting streaming data, from the windmills. We have this data stored, historical data stored, and we also have historical knowledge on at what point which turbine failed. We take all of this and we put it through a binary classification model, or through a binary classification algorithm, which produces a model that tells us that depending upon each field, whether a turbine is likely to fail or not. And this is what's in our ML model. And if you go, Kyle, if you scroll down, that's what you'll see, that we're building this ML model. Here we choose from a bunch of different options, which one optimizes the best for our outcome. But the final output here is that we have a ML model that's built from historical data that can just look at the 8 sensor readings and the speed of the windmill and predict whether it's going to fail or not. We're going to save that model. And then what we're going to show you next is, with a few commands, we're going to take that model and apply it to the incoming stream. So this was built from historical data. Now we're going to take the model and apply it to the real-time stream that's coming in. So within a matter of seconds, you could get a prediction with a confidence interval whether the turbine's going to fail or not. So let's walk through that notebook.
Yeah, so I've done my logistic regression here, which gives me sort of that one binary classification. And I've picked the best model, right? For those of you familiar with data science, usually try a number of different parameters and figure out the best model. And I'm going to go ahead and change that best one, and I'm going to save it to Azure Storage. So saving it to Azure Storage lets me create the model on one cluster, in this case, the cluster query cluster. And once it's on Azure Storage, I can then pick up that model from Azure Storage on my prod cluster to do the predictions. So I'm essentially going to feed that model back into my stream to do some predictions and identify which turbines might be in an unhealthy state that we might need to do maintenance on before they fail, and then load those results into Cosmos DB. So what I'm going to do here is just recreate my streaming data frame, just like we did in the first step. So same parameters, create the same data frame with the same schema. But in the part 2, I'm loading that model. So just in that same path where we saved it, I'm going to load that model, and I'm going to load the classes I need to load that model, and call this object pipelined model. Once I've created that pipeline model, it's going to read it from Azure Storage. I'm going to apply that pipeline model to my streaming data frame. And that's going to actually do the predictions based off of the sensor data that's coming in from the wind turbine to predict with some confidence of whether that turbine is in an unhealthy or damaged state. And so if we look at this output of this, we get to see we not only have our streaming data set that we're familiar with, we have all this other information which includes the output as well as the probability in that schema. So if I do a display on this, which I have running, if I scroll over, I get to see a bunch of information about the model itself, but really what I care about is this prediction on the right, a 0 or a 1. 0 meaning it's healthy, 1 that it's in an unhealthy state. So what we want to do is maybe we want to do some analysis on this in SQL. So again, I'm going to convert this to a SQL data frame because I know how to do the syntax a little bit easier in SQL. And we get to see what the predictions are. So as we would assume, most of the results are 0. We want most of our turbines to be healthy. And then some percentage, smaller percentage, is unhealthy, which is 1. And so we can see these numbers are also updating in real time. And so what we want to do is we want to break this out by a particular turbine ID. And so we see in this particular graph, I have 0 or 1 here. So in this particular turbine, turbine 2839, all of them are unhealthy. So this turbine might be in an unhealthy state. I need to go do some analysis on it if I need to go send some maintenance. Where this turbine has just a few. We only have a few out of the percentages of all the records are in an unhealthy state, turbine 19734. So with Spark Streaming, we can use that same aggregation that we were talking about. So every time a sensor throws a 1 in the prediction, you may not want to go alert your maintenance team. You may want to wait until you see some degradation of the sensors over time, or you see some number of positives over the course of an hour or a day. And so you can do that with Spark. You can do that aggregation over time. So I'm going to filter for where the prediction equals 1. and I'm going to write these outputs back to Azure Storage so we could do analysis on it. And finally, I want to load these to Cosmos DB. So Cosmos DB really powers the app that all my people who operate the wind turbines use. So I'm going to load in that failure data, identifying the turbines that have failed. I'm going to select which columns I want to write. And then I'm going to write that into my Cosmos database. So I have my configurations with my Cosmos key to config just like it's very similar to the Event Hub's connector. And all I need to do is take that data frame, do write mode. I want to overwrite. I could choose to append to Cosmos to this particular collection, failures, into the database turbine. And so these are going to be updated, so my application can now consume these results, and the engineer who needs to go do maintenance can figure out which particular turbines to prioritize.
And as we sort of, there was a lot of things in this demo, and depending upon whether you're super familiar with Spark, it might have been too much or too little, but the one thing that we want you to take away is, as Kyle walked through all of these steps, from reading data to building machine learning models, to analyzing the data, to applying the machine learning models and writing the output to an operational DB, at no point did you have to worry about what is the size of the cluster. Will it scale up or scale down? What happens if I have 3 turbines or if I have 3 million turbines? Your code remains the same, and our systems take care of scaling up or down. You've got to tell us, you've got to give us some limits on what you don't want to go over or under. But all of those things, all of those optimizations that you would have to think about are taken care for you. And that's the sort of the true power of Azure Databricks. This is one application. We were here to talk about streaming. We showed you some joins with batch, but this is one application. Like, you could build n number of things using this technology. So again, if you have never heard of Spark, then we encourage you to sort of try this out. If you are familiar with Spark, like if you already use Apache Spark in other places, we encourage you to try this out and let us know if our hypothesis that this is super simple is true or not. We'd like feedback both ways. But that's sort of our demo here. Just to sort of recap, we showed you Azure Databricks. It's best-in-class Spark. It's managed, which eliminates your DevOps. It's simple to use. The notebooks are built in. You don't have to write a bunch of command line scripts to add a bunch of libraries. Most things can be driven off the UI. It's fast. We didn't talk a whole lot about performance, but depending upon your workload, you can compare the performance with Apache Spark. You're going to see significant gains. Again, that's a whole another session. We could spend 40 minutes talking about that. We've built in flexibility for you to connect to any data source or sink. Right? You have data in the cloud, we'll provide you a connector to read it. We auto-scale and cost optimize. Like, as you guys, building is one part, but at some point you're going to want to go into production, and somebody is going to start doing bean counting and saying, this is what it costs to run this service. Is it providing enough value to me or not? We've built the service keeping those things in mind. We've built the service to scale up, scale down, auto-terminate. I mean, this might sound trivial, but just the auto-termination feature saves companies thousands to millions of dollars, because people have very, very large clusters. And sometimes humans make mistakes or scripts fail and they forget to turn off. You don't hit those problems with us. We've built in fault tolerance. Again, we didn't go into a whole lot of detail around that, but as you run these streaming jobs, there are a number of features that are built in to sort of accommodate when jobs fail and restart and where to pick them up from. So that's sort of what we were here to talk about. We have some time. We'd be happy to take any questions on what we showed, or even if there are questions on Azure Databricks in general around what we didn't show. We're happy to take those questions. And if you guys could use the mic, because this is being recorded, that would be very helpful. I see the gentleman in the green t-shirt. And sorry, just apologies. Before folks start leaving, because I know it's the last day, If you guys could also fill out our evaluation, that's very helpful to us. So if you're leaving before Q&A, please do help fill out the evaluation. Let us know how we did. Sorry, go ahead.
Yeah, just wanted to ask, you talk about different type of file formats that can be taken in. Do you have any kind of schema registration process also defined that can help us understand what streaming or what kind of data is coming and how we can make sure we understand that? So is there any registration process to help define what data we will accept through this pipeline versus we'll say we don't?
Yeah, so it's pretty flexible. Like depending on how you want to build the pipeline, you can specify a specific schema, and if the data comes outside of that schema, you can decide what to do with it. You can decide to quarantine it, you can decide to ignore it, and you can write that with a few lines of code. If you don't know what the schema is, there's different techniques to do that. So Spark handles complex types, right? It doesn't all have to be in a perfect type. So what you can do, and maybe you can clarify your question, what you can do is you can store data into like what we call a map type or in a string, and you can store the unknown fields there and pull out the known fields. So let's say, in our example, every wind turbine has a turbine ID, but not every manufacturer has the same number of sensors. What you can do is you can maybe have the schema or sensors you know about, extract them into a top-level column, and store the ones that you don't know about in a string or a map type, and have them there stored along with the data. So if someone wanted to extract that out, pull that out downstream.
So you're saying I could do that before I even start the process. I can map these data and have that specified in the process.
Yeah, that would be part of the processing, right? Because you got to look at the stream before you do some of those things.
That's what I was trying. So is that something like a gatekeeper or a process that we can go through before we even set it up, saying, okay, if somebody's sending me data, I want them to specify in this format or give me their schema so that I can look it up before I start processing it.
So if you wanted to look up the schema, you could get the schema in a variety of different formats, right? They could put the schema information in some sort of file that you could read, so that when the data is coming in, you want to convert it into that type of schema. So that part's very trivial. Like there is no automated way to get the schema. You can either allow our system to infer the schema, which we do a best guess on what it looks like, or use some. I think what you're saying is if I know the schema, can I enforce it? You could totally do that. And I think Kyle showed in the demo where he was like putting stuff into a given schema. How you get that schema is like an offline process. You could write the schema to a file and read it from there.
Yeah, and if you had the schema stored for, say you had 100 different sensors and you knew the schema for those, which is a common problem among our customers, you can store that in whatever format you want, JSON, YAML, XML, and we could parse that into Spark schema to handle that. So there's multiple ways to handle this. If you have a project.
But it's a very solvable problem. Yeah. To us, like that's really not a big deal unless we're missing something.
Yeah.
So Databricks is very powerful, but how do you compare Databricks with streaming analytic for this, connecting things from one data source to another, and also to visualize the results? Then we have a time series insight. So you can also run something in Databricks. So how do you compare those, and in which scenario we should pick up this or that?
So that's a very interesting question, and it really depends upon what you're trying to achieve and what are the constraints that you're working with. The first thing you asked is stream analytics and Databricks, right? The way to think about Azure Databricks is it's managed Spark, and stream analytics is just one part of what you would be solving, right? So depending upon your workload, if it's only stream analytics, then maybe you got to look at some other things like cost. What kind of expertise do you have in your company? What are the potential other things you're going to do? Customers often look at it and they say like, hey, I want to start with stream analytics, but maybe I want to do machine learning tomorrow. I want to use sparkling water models. Where is that available? And in that particular case, the answer would be Azure Databricks. There might be other cases which might lead you to stream analytics, but with Azure Databricks, you do get the general purpose Spark implementation, which can do everything that Spark does.
Okay. Yeah.
So I know that's not a perfect answer to your question, but it really is scenario dependent.
The thing, I guess, is similar things.
Could you speak into the mic, please?
So that's the similar principle for comparing Databricks and the time series insight.
Databricks and
the time series insight.
Yes, time series insights is a little bit more specialized into visualizing time series data. So I would say that certainly a number of things in time series insights that may or may not be available in Azure Databricks today. Again, it depends upon what you're trying to do, but time series insights does have certain things that are only available in time series insights. Okay. And we are, as we look forward, we are getting all this feedback from folks like yourself, from our customers, to see where the relevant integrations make sense. Okay. So this is a journey for us as well.
Okay, thank you very much.
Yeah, can Databricks Delta help with change data capture scenarios where you have like insert, update, delete streaming through from a database and maybe serving up an operational layer that business users can query?
Yeah, so I mean, Spark in general isn't like a operational database. It's analytical in nature. So for doing big analytical workloads, group bys, machine learning, streaming to get that data ready. For anything you need point lookups that's powering like a web app or any human in the loop, that's where you want to use transactional systems, maybe Cosmos DB. So kind of black and white, think of Spark as in the analytical space and those other engines in the transactional space. Should you do? That's why we've invested so much to integrate with Cosmos, because they really kind of serve completely different purposes for that. The Delta provide does allow you to do upserts, but if we peel the onion of what it's actually doing, it lets you find where maybe a key is, Turbine ID, and you need to update that, which files those are on storage, and has to rewrite those full files. So it's really meant for like updates that you may need to do. So not really high volume or high velocity that you might get in something like Cosmos, something that you may need to go back and change things. So
if you are sort of building a data warehouse, right? The pattern that we recommend is you do your big data analytics in Azure Databricks, leveraging Delta where needed, but your final serving layer is SQL data warehouse. So they do work with each other so much as against each other.
So I have a question on the SQL side. I see the example you have joined two tables. So in our case, we have a case like we join like 10 tables. And each table is like millions of, not all of them millions, some have millions of records. Mm-hmm. So do you have any performance data on those, or is Spark is not the right way to do this kind of thing?
No, obviously the best way to do it is to try it, and our team, the teams can help with that and dive into the specifics. But joining tens of tables is not a problem for Databricks, and it depends on the size of the volume. Small tables, get broadcasted on each one of the nodes. Bigger tables that can't be broadcasted to each one of the nodes, the data has to shuffle around the cluster. So there's different techniques to do that joining process, or even caching that data on the cluster. But most of that is transparent to you. So Spark usually figures out the most efficient way to do that join. So usually if you wanted to do that in like a stream and meet the SLA, you would just need a bigger cluster to be able to handle more joins. Another option, depending on the architecture of your use case, is maybe you do a few of the joins in the stream, but then after the stream's written, you can do a normal batch-based job that runs once an hour or once a day, do maybe some of the larger joins that need to happen, depending on the use case.
Yeah, that makes perfect sense. Do you have any kind of like a performance data you can share? May not be the exact same, but it's kind of give us some ideas.
TPCDS have joins
in
there. So yes, we'll share a link with you after the session if you don't mind waiting around for a little bit.
Okay.
Yeah,
sure,
if you search
Databricks
TPCDS, and we can share the link with you after. But if you forget, you can search Databricks TPCDS, and it does sort of the normal industry standard TPCDS benchmarks, which some queries are 1 join, some queries are 5, 10 joins.
Okay, great. Yeah. Thank you.
And all that data is available for you to run yourself if you want to try it out on Databricks. Okay.
Hello. Do you plan, you have Git integration, right? So the notebooks can be preserved in a Git repository. Do you have any plan of getting VSTS also?
Yes, absolutely. And this is, we always get this question, and we do have plans to getting that done. It's going to get done this year. It's not next month, but a little bit later. In the short term, what you can do is you can use the CLI tools, and we provide CLI tools to access all the notebooks. You can use the CLI tools to push and pull the notebooks from VSTS Git. But the Git integration that you saw, we're working on that for VSTS as well.
Okay, and when you do it, it's gonna be like with the authenticate with the key, or it's gonna have your account?
I don't want to talk about the design before I have done it, because if it changes, then you will, look bad. So.
Okay. So documentation-wise, how is the support and documentation work? Like there is a Databricks site where it's similar documentation that is the Azure Databricks site, and it's not on doc.microsoft.com yet, I think. So where is the...
that's actually an excellent question. This is a unique service in Azure, which is built with our friends in Databricks. Most of the other Azure, or I should say all of the other Azure services are built by Microsoft. This is the first one, it's a first-party service, so Azure supports it, Azure documents it, but it's built by Databricks. The documentation is on docs.azuredatabricks.net, and our slides, if I could go back, actually I put a link in there. So Databricks has a couple of documentation websites. It's also documented on docs.azure.com, which links to this website.
Oh, okay, so there is that one, and it's almost the same as the one that Databricks site has.
Yes.
Is it like, but it's not exactly the same.
It's not exactly the same, because
where should we go to see the latest?
You should go to this documentation webpage.
Okay.
But I hear your feedback that what I'm hearing is, hey, it's confusing. Can you guys fix it, please?
Yeah, because it's slightly different. Maybe I thought maybe some new stuff will appear on Databricks site, not on Azure Databricks. Or if we want to see the latest and what's going on, where should we go?
If you are using Azure Databricks, you should go on this website, and it should be always updated.
And that's updated by Microsoft or
that's
by
updated
Databricks?
by Microsoft and Databricks jointly.
Jointly. Okay.
Yeah.
All right, and support is through, again?
Support, you always call Azure support, and we work in the backend with Databricks as needed.
Okay, great, thank you.
Is that demo notebook available somewhere?
Sorry?
The notebook that you demoed, is that available?
We can make it available. We just ran out of time in posting it on GitHub, but we can make it available if you want to stick around and give us your email address.
So what are your plans for having this on Azure Stack?
So it's, again, we are open to input. As of right now, this is not available on Azure Stack, and I have nothing to share publicly, but we are certainly open to your input and trying to understand your scenarios on why and how it makes sense for you to be using Azure Stack and Azure Databricks together.
Sure. Probably we can discuss offline.
A real quick question. We do have HT inside that's in production. The question I have is, can I run the Databricks on the Kafka/Spark clusters we already have, or is it a separate service that I need to provision?
So the way to think about this is HT Insight offers you a number of different workloads. It offers you Kafka, it offers you Hive, LLAP, it offers you Spark. You can certainly use HT Insight Kafka and pipe that data into Databricks Spark. But the Spark part runs on Databricks' own clusters.
So I need to have, apart from the HT Insight, I need to have Databricks to make use of this?
Yes. If you want to run Kafka on HT Insight and if you want to run Spark on Databricks, you need to have two services.
I see. Thank you.
You also do have the option of running Spark, Apache Spark on HT Insight itself.
Which we have it already running. Yeah, I see. Thank you.
We're out of time, but if anybody has one last question. Thank you, guys.
Thanks all.